Now let's talk about epoxides. So epoxides are a specific ether. They are a cyclic ether with a three-membered ring. So we have a three-membered ring where one of the members of the ring is the oxygen. So we have an ether here. We have an oxygen bonded to two carbons, and those two carbons are also bonded to each other. Now, those two carbons are sp3 carbons. They can contain stereocenters if they're bonded to two different groups. So let's say we have an R group here and an R prime. R double prime, R triple prime. These would be two stereocenters. Now, if all of the R's are hydrogens, we don't have stereocenters. If they're all methyl groups, we don't have stereocenters. But this is what an ether looks like. This is what an epoxide looks like. And epoxides can be synthesized by treating an alkene, so carbon to carbon double bond, with something called a peroxycarboxylic acid. So we've seen the functional group carboxylic acid. Let's write a little note over here. A peroxy is when we have two oxygens bonded to each other. Now they can be bonded to other things. Two oxygens bonded to each other, we call that a peroxy group. A carboxylic acid is when we have a carbonyl. Carbonyl carbon is bonded to an OH group. A peroxycarboxylic acid is a carboxylic acid, so carbonyl, and that carbonyl carbon is bonded to an oxygen, which is bonded to another oxygen, so that's the peroxy part. And that terminal oxygen is bonded to a hydrogen. So we can synthesize epoxides by treating a alkene. We'll do an example of 1-hexene. Let me use a different color here. Go back to the black ink. And there's a specific common peroxycarboxylic acid that's used to synthesize epoxides. This is what we will see in our class. I'm sure there are other reagents, but we'll focus on this one. We have a benzene ring, a chlorine bonded to the ring, and in the meta position is the peroxycarboxylic acid. This is called meta chloro peroxy benzoic acid. For short, this is abbreviated as M, lowercase m, and then capital CPBA. Chloro peroxy benzoic acid. And the lowercase m is for meta. So this is a peroxy carboxylic acid. This is often done in the solvent of benzene. You may see other solvents. But as this reaction is carried through, we now have where the double bond was in 1-hexene is now an epoxide group, so that 3-membered ring with the oxygen, that ether. And then we have benzoic acid, or metachlorobenzoic acid as a byproduct. So metachlorobenzoic acid. So the alkene that's used for this reaction, we will definitely see that change. We'll look at different alkenes and what products are created by that alkene. But we'll often see the same MCPBA reagent and benzene solvent. We will look at the mechanism. It's a one-step concerted mechanism. There are a lot of things going on in this one step. This is a mechanism where maybe we'll talk about it in class. We'll draw the mechanism in class. It won't be on an assessment. So you should at least be able to use your notes as a reference to apply the mechanism to different molecules. But rest assured, I won't ask you to reproduce this without your notes. For the mechanism, just to keep it simple, I will simplify the alkene. So we have carbon to carbon double bond. And then each carbon we'll say is bonded to an R group and a hydrogen. And we'll have an E alkene here to emphasize stereochemistry. I suppose before we move on, it'll be helpful to look back at this example with 1-hexene and look at that epoxide product that we drew. In the 2 carbons that were part of the double bond that are now part of that 3-membered ring, this carbon here with that small purple arrow that I just drew, that carbon's bonded to 2 hydrogens, so there is no stereocenter there. But this carbon here is, which I just drew that arrow in orange, that carbon's bonded to a butyl group and a hydrogen. And the CH2 group as part of the ring and the oxygen as part of the ring. So this is a chiral carbon. That is a stereocenter, and when we form epoxides, both stereocenters form, so both enantiomers form. So now let's look at this mechanism and we'll see how that occurs. So I've drawn out that alkene. Now I'm going to draw that peroxycarboxylic acid. I'm going to start with the hydrogen at the end of the peroxycarboxylic acid with the 2 oxygens, and I'm drawing it in this way just to orient it in a way that's helpful to draw out the mechanism. I'm going to simplify the benzene ring with the chloro as R prime because that part of the molecule is not involved in the mechanism. So instead of drawing the L out, I'm just going to simplify that with that R. So we can really focus on where these arrows are, what these arrows are representing. Okay, so the oxygen to oxygen bond in any peroxy molecule is a weak bond. That bond is certainly going to break in this mechanism. The carbon to carbon double bond will create a bond to that terminal oxygen, so the one at the end of the chain. A few things are going to happen here now. The oxygen to oxygen double bond will break and form a double bond between the oxygen and that carbonyl carbon. Now that puts too many bonds on that carbonyl carbon. The carbonyl carbon double bond to oxygen will break and form a bond to the carbonyl oxygen. Now we have a single bond between that carbon and the oxygen. The oxygen, the carbonyl oxygen, will create a bond to that terminal hydrogen. And the electrons in that oxygen to hydrogen bond will create a bond to that carbon. I'm going to recolor two arrows because these two arrows are, let's see, I'll use green. These two arrows are the arrows that form the ring, and that's the two arrows between the alkene and the peroxycarboxylic acid. So the one from the double bond to that oxygen, and the one from the oxygen hydrogen bond to a carbon. The arrows are the same, just emphasizing them with a color. So now if we're drawing the products, we have our carbon to carbon double bond. I'm sorry, we don't have a double bond anymore. We have a carbon to carbon single bond. The double bond created a bond to the peroxy oxygen. And then the oxygen to hydrogen bond, these electrons are now shared between oxygen and carbon. And that's how we get our three-membered ring. Now these two carbons in the ring still have the R group and the hydrogen bonded to each one. And we now have an sp3 carbon, so we will draw these as stereocenters. Notice that the hydrogen on that top carbon and the R group on the bottom carbon, which are on the same side of the double bond, are now both on wedges. So that stereochemistry is preserved when we form the epoxide. Our other product is not the peroxy, but the carboxylic acid. So we now have let's say we'll start just to orient ourselves. We have the carbon and that bond to the R group did not change. The oxygen that was bonded the way we drew it above that carbon, the oxygen is still there, but it now has a bond to a hydrogen. So that's no longer where that carbonyl exists. We have the carbon to oxygen bond down here, and now this is where that double bond is. We have our electrons. So we have our epoxide with stereochemistry. Preserved. This is very similar to Diels-Alder when we had double bonds and then they became single bonds. We traced where substituents on the double bond end up as substituents in sp3 carbons in the product. So same sort of idea is happening here. So we have our epoxide with stereochemistry preserved, and then carboxylic acid.